Now, if you look at your class notes, there were a few animations listed there. I'm not showing those here because they don't play very well because they're getting older links. The best thing that you can do for muscle contraction if you're still struggling with it is to go on YouTube and just Google or search on YouTube muscle contraction animations. And you'll get ones from the textbook, or you can go on our textbook website and look at the video links. I highly recommend you check out some animations. They're really, really helpful just to kind of tie it all together. But we're kind of moving past that. So where does the energy for muscle contraction come from? Lots and lots of ATP is, of course, needed to keep you functioning. So ATP is your body's preferred method. But sometimes your muscle cells burn through that pretty quickly and need other sources. So muscles can use ATP, like all the other cells in your body. Muscle cells can also use creatine phosphate, which if you've ever worked out or gone to like one of those GNC vitamin stores at the mall, they have creatine powder. And then also our muscle cells can take glycogen, which remember is the storage of sugar. They can convert that into glucose and make ATP. So the point is muscle cells have lots of ways to fuel themselves. But, I mean, they're the ones using the most ATP in our body, so they kind of need to. This picture below, though, a lot of people find this confusing, is showing a sprint. The reason why we look at a sprint is because a sprint kind of shows us in a quick amount of time, usually 60 seconds or so, what muscles go through. So it's like a snapshot of what muscles go through. Sprints are not normal activities. Most of us do not sprint in our day. So sprinting is kind of going balls to the walls, giving it all you got, and burning through all of your energy sources. But it's just a nice little snapshot to see as muscle cells go through a sprint. So if you're doing an activity where you're running from a lion, tiger, bear, oh my, or you're sprinting, or you're giving it all that you have and you're not saving anything, you're not holding anything back, what would happen is during the first approximate 6 seconds, or the first few twitches as the muscles are warming up, ATP gets used first. So ATP is used for those things we just discussed, making and breaking those cross bridges. So remember, you have to use ATP to cock the myosin head back into place, like setting your mousetrap. But then ATP is also used to pull the calcium back into the sarcoplasmic reticulum. So I decided to try to draw that down below. Remember, we're swimming upstream. Remember, it's like trying to force kids back into the minivan at the end of the day. They don't want to do that. So to get those 2 calciums to go to the other side where there's 6, that's like forcing me to go from number 2 in line to number 6 at line in Walmart. We don't want to do that. So take some ATP. So use ATP first. Now, if you're still running from that lion, tiger, bear, oh my, and you've burned through all your ATP in 6 seconds, the next 6 to 15 seconds, you can make ATP in a really unique way. Muscle cells can do this. So remember when we talked about cellular respiration, how fun that was. In order to make ATP, we had to go through glycolysis, Krebs cycle, and ETS. That took time. It was complicated, and it was 3 steps. Well, if I'm running from a lion, tiger, bear, oh my, or I'm an Olympic sprinter, yeah, right, I don't have time for those 3 steps. So I have to depend on cellular respiration long term, but this is short term. This is going all out, giving it all I got for survival maybe. So what our muscle cells can do is they can take a molecule called creatine phosphate. And so if you look down below, I just kind of tried to draw it out simply. Creatine phosphate is a molecule of creatine that has a phosphate attached to it. So remember, you take ADP and you harness the energy from the food that you eat in cellular respiration to make ATP. Well, in this case, I could just rob a P from creatine and make ATP. So it's like a short, cheat way to squeeze just a little bit more ATP to get me through if I'm fighting. And the last thing that I can do is, after I have burned through all my available ATP from cellular respiration and all of my creatine phosphate that was stored in my muscle cells, I can take glycogen, which is stored in my liver for all my other cells, but muscle cells store their own. I can convert it to glucose and then go through cellular respiration. So I have kind of multiple ways, basically, as a muscle cell to get as much ATP. So oxygen. Where does oxygen come from? Well, of course, it comes from the respiratory system that we'll do next semester as you're breathing in. Hemoglobin. Hemoglobin. Heme means iron. Glob means protein. This is a protein that binds oxygen and iron. that holds these two things together. So this is what makes your blood red. It's what carries oxygen. So remember, muscle cells are very, very bloody. They have tons and tons of blood, bringing them oxygen. But another thing that muscle cells have is myoglobin. So myo means muscle. So these guys are really close relatives of each other. Myoglobin's job is going to be to bind oxygen and iron as well. So this is a protein that's in your muscle tissue. It should never, ever, ever, ever be in the bloodstream. If myoglobin is in your bloodstream, that means a muscle cell has been torn. It has been injured. Myoglobin is a special molecule that's in all of your muscle cells to kind of hoard more oxygen. So this does a lot of things. This provides the cells that they need, the muscle cells, with the oxygen that they need, more so for cellular respiration. So muscle cells are making so much more ATP, and the two things you need to make ATP, remember, are sugar and oxygen. And they have ways to cheat, muscle cells do, to get more of both of those molecules. We just saw that they store glycogen, which is sugar. Now we see that they have myoglobin, which gives them another way to kind of store oxygen. But we're not mad at them. They're the ones doing all the work. So we're not mad that they kind of cheat, because they need these things to make ATP. Another problem is when your muscles contract, sometimes it temporarily cuts off blood supply. And so this allows the muscle cells to store oxygen when their blood supply, which would be the oxygen coming from the hemoglobin, would be temporarily. So cellular respiration, we already spent our time on, remember. This is just kind of comparing the two. Aerobic respiration is always better. Oxygen is always better because, remember, you get roughly 34 ATP for every sugar. So you should be using this, aerobic respiration, during mild exercise, where you're breathing. And then your byproducts are carbon dioxide and water. I had a PE teacher tell us once that we should be working out enough to where we can talk, but not sing. If you can sing, you're not working hard enough. But you shouldn't be like, oh my God, working out, it's so hard, this treadmill sucks. Because you're actually not doing efficient cardiovascular exercise if you're sucking wind. When you start sucking wind, you switch to the bottom, the anaerobic respiration, which means you can't continue into Krebs cycle and the electron transport system because those require oxygen. So your body really just goes through glycolysis, the first step. And so you get, instead of 34 ATP, you get 2. That's not very efficient. And if your body's used to getting 34 and now you get 2, you're going to slow way the heck down. So this occurs after about 30 to 40 seconds of strenuous exercise when you're not breathing. You just get physically exhausted. You also start to feel the burn in your muscles because instead of just making carbon dioxide and water, you start making that lactic acid. But the benefit of anaerobic respiration is it's faster. I can at least get 2 ATP. If I'm running from that lion, tiger, bear, oh my, 2 ATP is better than nothing. But anaerobic respiration in the long run is bad because it leads to lactic acid and also what we call oxygen debt. If you're not breathing, you don't have enough oxygen to kind of get rid of that lactic acid that accumulated in the first place. So we call this oxygen debt, which is needed to take that lactic acid that you started making and convert it back to glucose. We also need to resynthesize all that ATP that we used in our strenuous exercise and creatine phosphate that we burned through, and replenish our glycogen. So if we've been running full speed, we have to take the time to repay those molecules that we burned up. We also want to make sure our tissue and blood oxygen goes back to pre-exercise levels. So what do we do to achieve these things? We pant like a dog at the end of hardcore strenuous activities. So sprinting, again, is just to show us a snapshot of what happens to your muscle cells when you go through an extreme situation. So from 0 to roughly 6 seconds, we're using aerobic respiration. We burn through our ATP. Then we use the phosphagen system, which was the creatine phosphate. So we rob that P from the creatine phosphate to make ATP temporarily. We burn through that. We can at least use our glycogen to convert to glucose to at least get 2 ATP from anaerobic fermentation. And eventually we drop and we start panting like a dog and we go back to aerobic respiration. But what I think is fascinating is you can actually train your body to do this chemistry in different ways. So if you're somebody that just casually works out, you wouldn't see this benefit per se. But there are people that do specific kinds of exercise and their physiology actually changes. So if you're an endurance trainer, if your aerobic exercise is to run like 6 miles a day, and some freak shows do this. I've seen it happen. I see these people running every morning when I'm on my way to Starbucks for a donut, you know. But athletes, long distance runners, they actually produce less lactic acid than normal people because they have trained their body so much. Most people don't wake up and just run 6 miles. They train every day. When you train your muscles and you're using your muscles more every day, they go, what the hell? I need more blood. So your capillaries, your cardio system, the capillaries are the smallest little blood vessels. They will actually branch out more. And also your mitochondria will divide more. Mitochondria, remember, are your ATP producers. They're your little powerhouses. So when you train, when you get into shape, you actually have more blood and more mitochondria, which both of those allow you to make way more ATP because you can get more oxygen to your muscles. So if you've ever heard the phrase, you got to have money to make money, well, in shape people have more energy. But it's kind of ironic because it's like, how the hell, if you're out of shape, do you have the energy to get into shape? But once you're in shape, your aerobic respiration is much more efficient. You make ATP a lot more efficiently. And so if you've ever gone from couch potato to exercise, the first 2 weeks suck. But after that, you do have more energy. But it's just, how do you survive those first 2 weeks? But once you do, your body makes more blood supply and you do feel more energized because you are making more ATP. But some people don't want that kind of training. There are some people that train for activities that rely on a surge of power. Not slow and steady wins the race for a 6-mile run, but sprinters, they just need, bam, so much energy really quick. Or swimmers, bam, or power lifters. So they actually rely more on that creatine phosphate reaction. So people that do powerlifting or people that do sprinting, their body actually gets better at storing creatine phosphate and relying on that ability to make ATP quickly. On and off activities are fueled more by glycolysis. Tennis. You know, if you've ever played tennis, you may stand there for a while, especially like partners tennis, and then all of a sudden you're like, bam, I have to go to work. Ah! Or like goalies. I've been to hockey games, because that's the only sport I really like, because there's like punching and stuff. I've been to hockey games where the goalie just kind of does nothing. Because if all the action's happening on the other end, he kind of just skates back and forth, like trying to keep his muscles warmed up. But then all of a sudden you have all these men coming at you on, you know, that are like 6'5" on skates with big sticks, and they look scary, all flying at you. So you need to be able to be intense, but then rest for maybe 10 minutes, and then intense, and then rest, and then intense, and then rest. So these athletes actually produce more glycolytic enzymes. Glyco means sugar, lyse means to split. If you just need that little burst every now and again, it'd be better to just be able to break glucose easier for 2 ATP. So the point is, every activity is a little bit different, and people that train their body to do one activity over the other will actually get better. Their physiology will actually get better at those types of energy burns. Most of us use all of these. But no matter what you do and no matter how good a shape you're in, you will ultimately fatigue your muscles. In lab, we've done that exercise where we held the lab manual out in front of us until our arms fatigued. Muscle fatigue is a state of physiology where the muscle cannot contract. There are lots of factors that go into muscle fatigue. ATP production just can't keep up. You're just burning way more fuel than you can possibly make. Lactic acid. If you're not breathing appropriately, lactic acid accumulates in the muscle cell. Ionic imbalances are present. Maybe you don't have enough of certain ions like calcium or sodium, whatever. The sodium-potassium pumps aren't doing their job fast enough. Maybe your sarcoplasmic reticulum is damaged and you can't get the calcium in and out quick enough. Maybe your acetylcholine is all used up. The point is, the result, get tired. Other things that can happen with muscles, a cramp. A few days ago, I woke up at like 3 a.m. with a Charlie horse in my calf muscle on the back of my lower leg, and I thought I was dying. If you've ever had a Charlie horse, I've only had like 2 or 3 in my entire life. It is one of the worst things ever, and my leg was sore for like 3 days. So sometimes muscles cramp, and sometimes extremely, like what we call Charlie horses. And I don't know why we call them Charlie horses, by the way. But this is a temporary involuntary muscle contraction. I think it's weird when sometimes you get like, cramp in your fingers or something from riding too much, and it's weird. This can happen because, again, a lack of ATP. Because remember, you have to have ATP to contract and relax. So sometimes your muscles will stay cramped up because you don't have enough ATP to reset those mousetraps, or for the calcium to come back into the sarcoplasmic reticulum. Again, an electrolyte imbalance. Maybe you don't have enough sodium. Low blood sugar. Acid, heat, drugs. Acid and heat, because remember, muscles are made of proteins and they can be denatured. Proteins don't like temperature. Excessive activity without enough oxygen can lead to cramping because you get a lot of lactic acid inside those muscle cells and they can't function normally. We always think that if a muscle cell can't function, it would be flaccid. It wouldn't be doing anything. But sometimes it can be a mousetrap in a contracted state. So if you have excessive fatigue, sometimes you can't relax your muscles. So you get this. This guy looks like he's having a really bad day. So without enough ATP, you can't get those calcium ions back into the sarcoplasmic reticulum, and so actin and myosin, the necklaces and the golf clubs, stay together. So it's all about energy. Sometimes, though, we don't get cramps, we just get weird little muscle spasms, which I always think these are funny, especially when you get them in like your arm muscle and you just look down and your arm's like jumping around all crazy. It's such a weird thing. But the place we tend to notice them mostly is in the eyes. We kind of go through phases where the little muscles around our eyes will sometimes twitch. Part of that is those are smaller muscles, and so when a few of the fibers start twitching, we just notice it more. And another thing is we're on all these electronic things all the time, and it fatigues our eyes more, staring at a computer and a television than ever before. But the point is, it's basically smooth muscle and skeletal muscle will get twitches. Thank goodness cardiac muscle doesn't get twitches. You wouldn't want your heart to twitch. So it's just that weird little thing that sometimes your little eye won't stop twitching. It just feels kind of awkward. In the face, we can call it a tic. So some people develop facial tics where they look like they're flinching all the time. This can be due to chemistry, of course. It can be due to physiology. But sometimes it's psychological. People will develop weird facial tics from, certain mental illnesses and things. Rigor. Rigor mortis is a weird thing. If you watch any crime scene shows, they always refer to rigor. Rigor is a stiffening in the body that occurs about 3 to 4 hours after you die. Now, the 3 to 4 hours kind of depends on the environment that you died. If you've ever heard of the Body Farm, which sounds terrible, but it's at the University of Tennessee, I think in Knoxville, they have this place where you can donate your body to science, and they just put you in various weird situations. Like they'll put your body just out in the middle of a field, and they'll record how long it takes you to decay. Or they'll put you in a basement and record how long it takes you to decay, what kind of insects feed on you, or they'll put you in a trunk of a car. Now, I know all this sounds kind of like a bad horror movie, but think about how beneficial that data is. If we find a body in one of those situations, we can now kind of figure out or how long you've been dead, what kind of situations you've been in. So this 3 to 4 hours is kind of like normal temperatures. If you're in freezing, it's going to take a lot longer for rigor. If you're in, 95-degree sun, rigor is going to happen a lot faster. So about 3 to 4 hours after we die, we see our muscles tighten up. It doesn't last forever, and a lot of people don't know that. It lasts about 72 hours or longer, again, depending on temperature. But it eventually goes away. But the reason why we call dead bodies stiffs, is because of rigor. Now, what causes this? Well, you start to rot. I mean, that's kind of gross, but think about if you left hamburger out too long. Not McDonald's hamburger, but raw hamburger that you meant to defrost and you forgot about it. It doesn't take long for that to get pretty skank nasty, okay? So you are protein, and proteins start to break down. So as our proteins start to break down, as our muscle cells start to break down, that sarcoplasmic reticulum can't hold the calcium anymore. So the calcium leaks out into that muscle tissue. Well, the calcium then sits on the troponin, causes the troponin tropomyosin complex to roll off that active site and causes a cross bridge. Because the reason why that works is because, remember, you put the energy into cocking that myosin head into position. So you've already put the ATP in before you died. So that guy just snaps up and causes the muscle to contract. But muscle relaxation can't occur because muscle relaxation requires ATP and you're dead. So we don't have any ATP to get the calcium back into the sarcoplasmic reticulum, so the muscle fibers stay contracted. The actin and myosin stay contracted until you start to rot. As soon as you rot, the body loosens back up again. One of the other byproducts of skeletal muscle contraction is heat. We kind of talked about this with the integument system, with the skin, how it was very important to curl into a ball to conserve your heat if you're cold, or lay all stretched out if you're hot, because a lot of muscles, a lot of heat is generated in muscle contraction. I mean, if you rub your hands back and forth, think about how much heat is generated. So then picture, millions and millions of muscle cells doing that. So only 40% of the energy is useful as work, like we saw with cellular respiration. Remember, with cars, it was only 25% of the gasoline actually pushes your car forward. The other 75% is waste. That's really depressing when you think about how expensive gas is. Same thing with food. Only 40% of the calories in your food actually do work in your body. The other 60% is heat. So we've got to get that heat out. It radiates from our skin. We also sweat because we don't want to literally cook